How's it going, ladies and gentlemen? Mr. Donnie here again. This time we're going to take a look at some 24.3 practice problems: unsaturated hydrocarbons, addition, and aromatics. So number one, which of the following statements is not true about addition reactions between alkenes? So remember, alkenes, we have that double bond there. Let's see. Does addition occur at the double bond? This is a true statement. It sure does. B, bromine attacks the alkene carbon atom that has a partially positive charge. This is also true. Think about bromine being a nonmetal is going to have a partially negative charge. It's going to be attracted to the region on the molecule where it has a partially positive charge. So that's a true statement. The mechanism involves radicals. This is not a true statement. All right, let's check the rest of them though. D, a hydrogen atom attaches to the alkene carbon atom that has a partially negative charge. This is also a true statement. We know hydrogen likes to have a positive charge, so it's going to be attracted to the region that has a partially negative charge. So that's a true statement. And E, the pi bond breaks during the reaction. This is a true statement, right? So one of those two bonds in a double bond is a pi bond, and that's the one that breaks in order to make new bonds with whatever's being added to it. So correct option is choice C. All right, number two, what kind of compound is shown below? So the thing that should jump out at you is this double bond, right? That means it is an alkene, right? We have a double bond. If there was only single bonds, it'd be an alkane, or it's just single bonds. And if there was a triple bond, we call that an alkyne for triple bond. So which one is it? It's the alkene. We have a double bond right there. Although, like, this molecule is broken, isn't it? Here's an error. CH, CH3. This one only has H. That should be an H2. Anyway, because of this double bond, go alkene. Number three, how many structural isomers, excluding optical isomers, but including cycloalkanes, can be drawn for C5H10? So, C5H10 follows the CnH2n, which tells us that we can have alkenes, or we can also have cycloalkanes. So let's see what we can make using just these parts. Well, the easiest first one probably be pentene. So this is called 1-pentene, right? Because we have the double bond after the first carbon. So we got 1-pentene. Could that double bond be somewhere else? It sure could. It could be after the second carbon. So we'd have 2-pentene right there. Could we put the double bond somewhere else? Well, if you put it here, it's the same as putting it there. So that's really the same molecule. Same with if you put the double bond here instead, it's the same thing as this first one. You're just looking at it from the other side. So another way to do it is, hey, let me take that fifth carbon and put it on one of those middle carbons. So now I have 1, 2, 3, 4 carbon chain. So that's bute, double bond, ene. The double bond is after the first carbon. So I got 1 butane or butene with this methyl group on the second carbon. So we have 2 methyl, 1 butene. All right, I can have the same kind of parent structure, but move that double bond to somewhere else. So again, this is still after the second carbon for the methyl group, and also after the second carbon for the double bond. So we have 2 methyl, 2 butene. All right, so what other ways can we do this? Well, we can put that double bond at the end. Well, how is this different? Let's see, we're going to have to number it right to left. So this is 1, 2, 3. So we have that methyl group on the third carbon. So I have 3 methyl and that double bond after the first one. So 1 butene. That's not an E, it should be a U. That's how you spell these things, don't you? So we have 3 methyl, 1 butene. We also have, hey, what's going on here? Well, I have a ring right here. So we have cyclo, and it's 4 carbons. So I have a cyclobutane because it's all single bonds. And then I have this methyl group. So I have methyl cyclobutane. And I don't really need to put a number there because it's a circle. It's on one of those carbons. There's nothing that makes them different from each other, so numbering it doesn't really make any sense. So I have methyl cyclobutane. I could also have, hey, here's a cyclo group that's only 3 carbons. So I have cyclopropane, and now I have 2 dingly-danglies. I got 2 methyl groups, so I will have to number them. So how do I say I have 2 methyl groups? I have dimethyl. And where are they? Well, if you just pick, if this is the first one, then that's the second one. So I have 1, 2 dimethyl propane. I forgot the H there. What else could you draw? I could draw this. Those 2 methyl groups could be off of the same carbon here. So I still have cyclopropane. And it's still dimethyl. But they're both on the same carbon. So 1, 1 dimethyl cyclopropane. Any other ones that I can make? Yeah, there sure are. Here again, I still have this cyclopropane right here. And now I have a 2 carbon chain, an ethyl group. So I have ethyl cyclopropane. And then is there another one? I think I might have gotten them all. Oh no, I forgot about that one. Right here, let me erase this. How could I forget the single easiest one? This, it's a cyclo closed ring, 5 carbons. So we have cyclopentane. And I guess technically the question is just asking how many structural isomers are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I guess would be the answer, but that's what they all are. Number 4, name the following compound, and then here it is. And then note that the bonding isn't shown in this abbreviated formula. So we have like a condensed structural formula, so you got to draw it out 1 carbon at a time. I have CH3, so C, 3 H's. I have CH2, boom, boom. I have CH. I have another CH, and then I have a CH2. And then I have a CH, and then another CH, and then a CH3. So now you may be seeing something that's funky. It's like, hey, what's going on here? Those carbons only have 3 bonds. Exactly. What they're not showing you in this condensed abbreviated formula is that there's a double bond there. But you can figure it out because you would expect there to be another hydrogen there. There's not. Why is that? There's a double bond. And it's also right here. So let's name the chain. How many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. So I say oct. And then, hey, wait a minute, there's 2 alkene groups. So we say octadiene, where the di means that there's 2 of them, and the ene means that there's a double bond. And then we got to number them. So let's see, if I go 1, 2, 3, counting that way, or 1, 2. All right, so I'm going to want to count right to left. So I have 2, well, let's keep going, 3, 4, 5. Double bond is after the 2nd carbon and after the 5th carbon. So it's 2, 5 octadiene. Cool. All right, number 5. What is the name of the following compound? So again, we've tried to find the longest chain. I'm hoping that this part jumps out to you. You know it's not going to be, this 1, 2, 3. You know that isn't the longest possible chain. So the longest possible chain is probably this straight line going left to right. And then what do we got going on? Well, we have a triple bond and we have 2 methyl groups. So first, let's count the carbon chain. 1, 2, 3, 4, 5, 6, 7. How do I say 7 carbons? Hept. How do I say that there's a triple bond? Ine. So I have heptine. Where is that triple bond? Well, it's either going to be after the 6th carbon or after the 1st carbon. So I have 1 heptine. Now I got to name these dingly-danglies. I got 2 methyl groups. So I have dimethyl. And where are they? Well, I already decided that I have to count left to right. The 1, 2, 3, it's on the 4th carbon and on the 5th, 6th carbon. So I have 4, 6 dimethyl heptine. Dimethyl 1 heptine. There you go. Number 6, which of the following statements is false? So with these kind of problems, I always mark true or false for each option and then go back because sometimes which one of these is true, which one of these is incorrect, and I get it messed up. All right, so alkanes can be created by hydrogenating alkenes. This is a true statement. The smallest alkane to have a structural isomer has 4 carbons. This is also a true statement, right? Propane with 3 carbons, you can't put together any other way. Butane, you can. C, alkenes have cyclic alkane isomers. This is true, right? In the previous problem where we had to draw all of them out, you could see that, hey, in the alkenes, you can either have a double bond or you can make an isomer that is a ring. All right, what about choice D? Alkenes can be polymerized via addition polymerization. This is true because they're alkenes. You can break that double bond and then have it bond to another alkene whose double bond has also been broken. And then E, alkanes are more reactive than alkenes. This is the false statement. So a single bond more stable than there being a double bond. All right, so which one of these is not like the others? E, it is the false statement. 7, draw cis-2-butene and trans-2-butene. Cis means same, trans means different or like across. So if we're drawing butene, 2-butene, I know that I have a carbon double bond in the middle, and then cis means that the hydrogens are going to be on the same side. So I can have hydrogen both on this side of the double bond, which means the other carbons are off this way, and also on the same side of the double bond as each other. So this is the cis configuration. Trans would look similar but different. So the hydrogens are going to be on opposite sides of each other, and the CH3 groups are going to also be on opposite sides of each other. So this would be the trans configuration. That's it. All right, hope you found it helpful. I'm seeing you in class. Goodbye.